As is well known, stars primarily emit light and heat through internal nuclear fusion. However, in recent years, scientists have speculated that in the early universe, there might have been a class of stars that were unusually massive but lacked internal fusion. Instead of ordinary matter, these stars were powered by dark matter within them. Due to their low surface temperatures, we would only observe faint light emitted from them, leading scientists to term them dark stars. As previously mentioned, current cosmological models still have some issues, such as the unexpected maturity of early galaxies and the rapid formation of supermassive black holes. To address these problems, researchers are pursuing two main directions: patching specific problems or fundamentally revising the cosmological model. The recent concept of the cosmic doubling falls into the latter category, while the topic of discussion today, the dark stars, belongs to the former. Stars are classified into three generations, based on the proportion of metal elements they contain. Note: in astronomy, metals usually refer to elements other than hydrogen and helium. The term generation here doesn't strictly imply generational shifts, it's more about age ranges. Our Sun belongs to the youngest generation, akin to the grandchild generation, containing materials processed through several stellar generations. These stars are called the first generation. Stars of the generation before, second generation, have even fewer metals, primarily originating from supernova explosions of first-generation stars. The earliest stars after the Big Bang, with almost no metal elements except hydrogen and helium, are the third generation, akin to the great-grandparent generation. Currently, first-generation stars are common, second-generation stars are occasionally found, but third-generation stars have yet to be discovered. However, in 2007, scientists proposed an even older star than the third generation. Strictly speaking, these stars can't truly be called stars, as they lack nuclear fusion. This implies that they don't fit the conventional definition of stars. But viewed from a different angle, they might represent the genuine first stage of stellar evolution on a cosmic scale. Hence, they can be referred to as primordial stars. During the onset of the Big Bang, as hydrogen and helium began to form, the skeletal structure of matter composed of dark matter was already taking shape. Under the influence of dark matter's gravity, hydrogen and helium particles started to coalesce around this structure, resembling flesh forming on bones. Subsequently, galaxies started to form in regions with higher concentrations of dark matter. In the centers of these galaxies, where dark matter was denser, hydrogen and helium accumulated, growing in size and quantity over time. Although this cloud of gas was initially triggered by dark matter, as hydrogen and helium gathered, the proportion of regular matter gradually increased. This continued until regular matter constituted over 99.9% of the gas cloud. At this point, the mass of the gas cloud could reach millions or even tens of millions of times that of the Sun, with a diameter exceeding thousands of astronomical units. Even the enormous star Stephenson 2-18 would seem diminutive compared to it. Comparatively, third-generation stars at most have a few hundred times the mass of the Sun. For an astronomical body with millions of times the mass of the Sun, it should have undergone gravitational collapse and initiated nuclear fusion at its core long ago. However, the presence of 0.1% dark matter within it leads to a different scenario. Dark matter, still not fully understood, could be one entity or the combined result of various interactions. Researchers have focused on a candidate particle known as the neutralino in this study. Neutralinos, hypothetical particles predicted by supersymmetry theory, are electrically neutral fermions, sometimes referred to as Majorana fermions. When these dark matter particles, composed of neutralinos, reach a high enough density, their self-annihilation produces gamma rays and high-energy particles. Numerous dark matter detectors aim to capture these specific electronic or gamma ray signatures to indirectly discover dark matter particles. Returning to the topic, the reason the massive gas cloud didn't initiate nuclear fusion in its core was due to the annihilation reactions of dark matter particles within it. Under normal circumstances, the gas cloud should have collapsed under its massive gravity. As the core density and pressure grew, quantum tunneling could have initiated nuclear fusion between hydrogen atoms, sparking the process. However, the inclusion of annihilation reactions counteracted the inward gravitational collapse, preventing the initiation of fusion. Consequently, the gas cloud exhibited characteristics similar to stars, yet significantly different. Similarities included the ability to emit light, although not through nuclear fusion. Differences arose from the incredibly faint light emitted, albeit relative to its immense mass, due to its very low temperature. In general, a star's brightness increases with its mass. For example, our Sun's surface temperature is around 6,000 degrees Celsius, while the dark star, despite being millions of times the Sun's mass, has a surface temperature of merely 10,000 degrees Celsius. This relatively low temperature generates dim light, earning it the name dark star. To clarify, a dark star isn't a star composed entirely of dark matter. While dark matter does play a role, it merely provides an energy source for this type of star. With only 0.1% of dark matter contributing to energy generation, the dark star's temperature remains low, resulting in a lower luminosity. However, its enormous mass ensures a significantly high overall luminosity, potentially reaching billions of times the Sun's luminosity. Thus, with sufficiently advanced infrared detection capabilities, we still have a chance to discover them. Indeed, in June 2023, an article published in the Proceedings of the National Academy of Sciences reported the discovery of 3 potential dark star candidates among several hundred high redshift objects observed by the Webb telescope. Currently, the analysis primarily focuses on their luminosity, lacking strong evidence. Researchers plan to conduct detailed spectral analyses of these 3 candidates to confirm whether they exhibit characteristics aligned with dark star theory. If dark stars do exist, what problems can they solve? As the minuscule amount of dark matter within a dark star depletes, ordinary matter continues collapsing inward until nuclear fusion is initiated. For smaller dark stars, this may be favorable news, as they could eventually transition into genuine stars through fusion. This marks the advent of the universe's first true stars, the 3rd generation. However, the situation isn't as optimistic for massive dark stars. Their immense mass ensures unstoppable gravitational collapse, rendering the energy from nuclear fusion negligible. As a result, all matter collapses into a singularity, forming a black hole millions or even tens of millions of times the Sun's mass. As seeds for supermassive black holes at the centers of galaxies, these black holes derived from dark star transitions indeed provide a solution for the rapid formation of massive black holes. Thus, a new possibility emerges regarding the origin of supermassive black holes.